Welcome to the STEM Pathways with Rohan Sharma podcast, where we dive into the exciting world of science, technology, engineering, and math. In each episode, we share exciting stories, groundbreaking research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing John Cressler, who is currently a professor at Georgia Tech. How are you doing today?
I'm doing wonderful. Thank you.
Yeah, so to get started, I wanted to ask what were your interests in high school and how did you choose your major for your bachelor's degree?
Yeah, it's a great question. And so I'm interested in all things I don't know, believe it or not. So I have a great love of literature and history, but a particular love for mathematics and science. And during my junior year of high school, I had a particularly transformative event, and that was to have a calculus teacher, Dr. Don Dormany, who was took me under his wing, seeing, I suppose, a little bit of potential and gave me lots of hard problems. And I think he was very interested in connecting mathematics and physics. So, how math actually tells us things about the physical world. And that resonated with me deeply, actually. So, at that point, I became hooked on both math and science, and particularly physics and calculus. And it was really the first time, I think, in my life that I was able to see the power of mathematics to help us understand the natural world. And that I found absolutely riveting. So when I finished high school, I knew I wanted to study physics. And so Georgia Tech was right here. I grew up in Atlanta. And so it became a very natural segue for me
Yeah.
to move forward.
So what was your experience like while at Georgia Tech?
Well, it's interesting. I fell in love with physics, but it was kind of an interesting discovery. I had to pay my way through college, uh, which was a great experience for me actually. And so I started my freshman year co-oping to pay for my next semester at Georgia Tech. My family comes from rural North Georgia and of humble means, and so I was actually got placed in my co-op assignment in a semiconductor device research team at IBM up in North Carolina in the Research Triangle. And I immediately fell in love with semiconductors and semiconductor physics. And that gave me then a segue to enter the world of high-speed electronics, which is kind of what they were talking about at that time. So even as say a sophomore at Georgia Tech, while I loved my physics and was taking all the math and stuff that I could find, I did a crazy thing actually. I started taking all of my free electives in electrical engineering because that's where a lot of the research was happening in the world of electronics, right? And so I held on to my physics degree, but also I didn't double degree in double E, but I certainly took all of the electronics focused electives that electrical engineering actually offered. And so that set me up well. So I had a great experience here. I mean, I think if you're in the right university and you're studying the things that you love to do and you love the process of learning, even when it is, high stress and a lot of work, it becomes very rewarding because I could kind of directly see in my interactions with co-oping how this would play for the world, right? And where future research possibilities might go. So at that time, actually, I pretty much assumed I would go ahead and do my PhD in physics and focus on semiconductors and semiconductor devices and try to transform the electrical engineering world. But I was madly in love with my high school sweetheart, and we wanted to get married. And so I put that on hold and decided to get a job and then go back and get my PhD later. Interestingly enough, I was able to land a job, actually my dream job, at IBM Research in New York State, or just north of New York City, Thomas J. Watson Research Center. Without question, the leading industrial research laboratory in the world, right? Typically, you have to have a PhD to get in there to work, but they saw something in me that they liked, and so they brought me in, and I made the transition then in working in a very advanced exploratory research team in electronics, right? And so I was doing the things, excuse me, I was doing the things that I had always wanted to do, and So that, and then they had, fortunately, a program where it was a highly selective program, but they would you maintain your work at IBM Research, and they gave you time off and paid to go get your PhD. And so I did that at Columbia University, and the advantage for me was I was able to use the research laboratories at IBM Research, which were world class, to do my thesis research, right? So it kind of sped up the whole process there. So that's kind of bookended my life's trajectory. I got involved with a research team that had pioneered how we build transistors. And just to step back for your audience, in high school you may or may not be exposed to this, but in 1947 was the invention slash discovery of the most transformative thing that has ever embraced planet Earth, and that's the transistor. So think of that as an on-off switch with amplification properties done in a crystal material system, right? There's not a single piece of technology that any of you use currently or will ever use that don't have transistors in them, right? And so what we were engaged in at IBM Research, and I'll say more about my PhD research in a moment, but we were engaged in how to take, I'll show you some props here, how to take a silicon wafer, which drives the world's economy. This is actually it's a scaled replica of the world's first transistor that was done at Bell Labs in 1947. And so that's what's transformed the world, right? So you've probably heard, the audience has probably heard of Moore's Law or the exponential growth patterns, which are completely without precedent in the world today, but they're very recent phenomena. And what that says basically is that if you've studied a little calculus, you'll know that exponential functions are the most rapidly changing in nature. So you go from small to huge very quickly. And in the case of integrated circuit technology, transistor technology, computer technology, we go from nothing to something very powerful, think AI, at the same time that it's getting exponentially more powerful. At the same time, it's getting exponentially cheaper to do that power, right? And that's what's fueled the world's economy. That's a multi-trillion-dollar industry, all driven by the things that we do in STEM and electrical engineering and physics, right? So that's been very transformative. So when I was at IBM, what we were looking on is silicon is an incredible manufacturing platform, right? And the world's integrated circuit and transistor manufacturing is again a trillion-dollar industry, and the idea can we do that better, right? And so the way you do that is to stay in the silicon material system, which is a semiconductor, but now use nanoscale engineering techniques using a different semiconductor, germanium in this case, to uh, maintain the economy of scale of silicon manufacturing and all that that means: bigger, faster, cheaper, but do it much better, actually, right? And so think of taking the raw speed of a transistor in 2025 and doubling it or tripling it without adding any cost to the process. Again, that's a model which has never been demonstrated. I was fortunate enough as a young engineer slash scientist to be a part of that journey. And then when I decided to make the jump to the academic world, I'll give you that story in a moment. It might be interesting to the audience. Um, I've kind of ridden that horse my entire research career, which is now 33 years as a professor and 8 years before that at IBM Research, right? So that's now branched from the highest speed transistors today has that field of my own in research has I do a lot of work in space systems, space exploration, the intersection of electronics with radiation phenomena and the radiation belts of Earth, from exploration of the moon and Mars and outer planets. And I also look at the impact of temperature on these types of devices. So that touches the whole field of quantum computing and quantum science, right? Which is also a very hot field and it's going on. And then more recently, it's expanded to what's known as silicon-based photonics. And so now if you imagine electronics would be this silicon wafer that I just showed you, switching so in 2025, viral size transistors switching at nearly the speed of light. We work to make that even better. And now I want to bring light, photons down onto the surface of silicon, right? And so that's being done as we speak. And I'm again very interested in a couple of things in that context. One would be how do we use these in space systems, right? So if you think of the nearly 6,000 satellites that are up in space that are doing everything from communications to climate science, they're aggregating with their sensor systems tremendous amounts of data. And the question is, how do you move that around, both on the spaceship, the satellite, or getting it back to Earth so we can manipulate that? And so photonics is a great way to do that because in a photonic system, you have nearly infinite bandwidth for moving data about, right? So that's kind of a long story short. That's kind of my career is in this field of silicon germanium technology, which is an electronics, photonics, low temperature space exploration. Everyone's smartphone has amplifiers built from this in it. It's done worldwide today, and I've kind of ridden that wave as I've gone through my career, which has been great fun and very rewarding, actually. So let me just fill in one missing piece there, and that is, how and why did I make the transition to be a professor? And I think that's a lesson for anybody in high school aspiring to make a difference in the world, is something I would say. So back when I was a young researcher at IBM, my wife and I were married at that point. We had little kids running around, and we needed money. We're living in an expensive area of the world in Connecticut. And so one of my good friends told me that they had a teaching position, adjunct teaching position at the university at night, teaching calculus, which was my first great love, right? First and second year calculus. And so I was first not interested in that, but then I finally decided to do that. And literally that transformation, when the first time I walked in front of my own classroom, it hit me like a ton of bricks that that was my life's calling, was to be a teacher, right? And so this notion of teaching, and when I say teaching, I mean in its broadest possible context. And hopefully you have good teachers, meaning not just that they know their material and they're educated and they know how to teach, but there's a large mentoring aspect that comes with that. How do we identify our gifts and bring in those gifts to the world to make a better place, right? So about 33 years ago, I made that transition from my beloved academic research to, my beloved industrial research to the academic world. And so now I teach undergraduate and graduate courses in this field and mentor students and run a large research team aimed at pushing the boundaries of electronics and photonics using these silicon germanium nanoscaled engineering problems.
Yeah.
So that's kind of me.
So, right now you're a professor at one of the biggest, or like most prestigious engineering universities, and
Yeah.
you guys have the most engineers, out of any university, the biggest engineering college. What's it like having so many resources and having so many students available to you versus researching at a different university?
Yeah, it's great. Well, I've actually kind of seen both worlds. So when I jumped from IBM research into the academic world, I started my career at Auburn University, which is a good school, but now it's not a Georgia Tech, right? And so it's about 2 hours from here. And so I got off the ground and figured out how to teach and do research, and we were doing fun things. But uh, interestingly enough, I one time ran into one of my former Georgia Tech professors on the plane in San Francisco, getting on the plane there, and he was reminding me that Georgia Tech had changed a lot since I was an undergraduate, and that I should come over because they wanted to talk to me. And so, 23 years ago, so I spent 10 years at Auburn, and then 23 years ago came to Georgia Tech, and it's been a great ride. As you say, it is a top engineering school, so the talent level of students, both undergraduate and graduate, is stellar. And I think the resources and infrastructure are stellar. And what that does for capable people is, both student and professor alike, is to allow you to really knock on and open any door you want to, right? So professors have a lot of freedom to do the kinds of exploratory work that they want to do, and this place enables that actually, right? So electrical engineering here is one of the largest departments. There's about 100 faculty, right? And gosh, almost 3,000 students if you count undergraduate and graduates. It is the largest program in the country, and it's a fun place. I got to tell you, it's a high pressure place because you're working now, and this would be, I think, useful for folks at the high school level to think about, right? Is when you're in a very competitive environment, it brings out the best in you if it resonates with you, right? So working around, I mean, you walk into this place and everybody's as bright or brighter than you are, but there's this energy and this desire to innovate and make a difference and discover and do. And you're able to do that here, right? So Georgia Tech, I'll just say, is filled with what are known as maker spaces, and you probably are familiar with that term. These are basically laboratories that are staffed and run to enable students to walk in off the street with zero experience and get trained how to make anything they want to do, right? So a bunch of those exist across campus. Electrical engineering has a couple of those, one of which is, it's an electronics makerspace. So you can come in and build anything that's got electronics in it. If you need to 3D print or build a board or whatever, yeah, they do it all there for you for free. And now just this last year in 2024, we launched the world's first, to my knowledge, the world's first AI makerspace, right? So NVIDIA donated a massive computational cluster we have a data center here, which is probably sucks most of the electricity from Atlanta, but it's huge. And now students can get access to that and kind of do anything they want exploratory wise, right? And there's of course a big push here in entrepreneurial stuff, right? So a student there are numerous programs on campus to allow even undergraduates to team up and start their own companies, right? And they give you space for that and funding for that. And of course, the maker spaces provide any of the background infrastructure that you need to do that. So long story short, it's a fun place. Competitive, yes, but I think the best and the brightest of the high school students that might be watching a YouTube channel like this, you should aspire to be with the best and the brightest because it's going to open doors for you. It'll be stressful, no question about that, but it gives you a rare opportunity to do things you wouldn't get to otherwise. And I think always, in my view, the way I like to talk to students here is, when you get done with this place, you, you're going to have the opportunity to be a mover and shaker in the world. And that's exciting, but also brings with it a layer of responsibility that is awfully important, right? Meaning you need to think about not just whether something can be done, but can it be done in a way which is good for the humanity of planet Earth, right? And our planet as well, right? So I think those things are very big here, right? And so that's this place. It's a fun place, no argument.
Yeah, so for my last question, I wanted to ask if you have one piece of advice for someone who's still in high school or early in college wanting to follow a similar career path as you.
Yeah, I think the advice I would have might sound a little weird, but let me give it anyway. It's to fall in love with a topic, an area of research, an idea. And, for those aspiring to STEM, of course, math and science are big, but they're not the only things, right? I am always pushing students that are hardcore math and science to broaden out into literature, into history, to do these things to broaden your skill set. So, yes, fall in love with the technical areas that bound STEM, uh, but also fall in love with the things that may seem tangential, literature, history, the softer arts, I think, and leverage those. Be a reader, right? But not just reading technical books, read fiction. And I'm a writer of fiction, and so I fully embrace that path. And I think the other advice I would give would be for those aspiring to STEM world to be an innovator would be get your hands dirty, meaning build things, take things apart. I mean, ask permission from your parents first, but take apart something, whether it's a toaster or a TV or an old computer or an old phone or whatever that might be. Figure out how they work. If it's building a piece of electronics or building a robot or building a rocket or whatever that might be, that kind of hands-on, often collaborative enterprise of seeing how things work and wondering how things work, because that's how you know how to make things better, right? And so, yeah, hands-on, not all book learning, not just science and math, but everything else. Those are kind of my pieces of advice. And aspire to make good grades, of course. You need good grades, but that goes without saying.
All right, then. Thank you for joining me on the podcast today.
Yeah, my pleasure. And I'm easy to reach if anybody has further questions. And thanks again, Rohan, for inviting me to speak.